design a shear reinforcement for a beam of 8 meter span having 30 kilonewton per meter UDL. Beam size is 300 mm by 610 mm overall depth, 30 mm effective cover. To stop. The reinforcement consists of 6 bars of 25 mm diameter. To stop. Concrete is M20 grade and steel Fe415 grade. Okay. So first of all, write down the given data for that. So span it is given L is equal to 6 meter. L is equal to 6 meter. And UDL loading it is given W is equal to 30 kilonewton per meter. Then beam size it is given, width of beam it is B is equal to 30 mm. Width of beam B is equal to 300 mm. And overall depth of beam it is given, that is means capital D it is equal to 610 mm. Then effective cover it is given, that is D dash. D dash is equal to 30 mm. Then the reinforcement consists of 6 bars of 25 mm diameter. That is means AST is equal to 6 bars it is given, 6 into diameter of bars it is 25. Then area for circular bar it is pi by 4 d square. Pi by 4 into 25 square. Pi by 4 into 25 square. Pi by 4 into 25 square. The area of steel in tension we get. So 6 into pi by 4 into 25 square. It will be, so this value will be 6945.243 mm square. Okay. The area of steel in tension it will be 29. So 2945.243 mm square. Okay, so I will note down this value. AST is equal to 2945.243 mm square. Okay. The next that it is given, the concrete is M20. That is characteristics of compressive strength. It is FCK is equal to 20 Newton per mm square. Okay. Then grade of steel it is Fy is equal to 415. Fy is equal to 415 Newton per mm square. 415 Newton per mm square. So this data it is given for design of shear reinforcement. Okay. So first step, calculate factored shear force. Step 1, factored shear force. Step 1, factored shear force. Step 1, factored shear force. Shear force. That is V. Factored shear force, that is in bracket VU. Okay. The actual beam it is simply supported. This beam it is simply supported. Span it is 8 meter. Span it is given 8 meter. And UDL load it is acting on that beam. That loading it is 30 kilonewton per meter. 30 kilonewton per meter. Total span it is 8 meter. So shear force means reaction of this beam. Okay. This one it is support A and this one it is support B. So maximum reaction for this at A and B it will be WL by 2. So RA it is WL by 2. That is means shear force. Maximum shear force it is WL by 2. Okay. So V is equal to WL by 2. W into L it is span of this beam is divided by divided by 2 divided by 2 divided by 2. Okay. So W it is UDL loading, it is given 30 kilonewton per meter, 30 into tan it is 8 meter divided by 2 divided by 2. Okay. So we get shear force, maximum shear force 30 into 8 divided by 2. It will be 120 kilonewton. 30 into 8 divided by 2, it is 120 kilonewton. 120 kilonewton. So factor shear force VU is equal to V into 1.5. V into 1.5. Factor shear force it is 120 into factor of safety is 1.5. Okay. So VU factor shear force is equal to 120 into 1.5. It will be 180 kilonewton. 180 kilonewton. Okay. So factor shear is 180 kilonewton. So I will note down this value also. VU is equal to 180 kilonewton. Okay. 180 kilonewton. So now step number 2, nominal shear stress. Step number 2, it is nominal shear stress. Step number 2, nominal shear stress. Nominal shear stress. That is, it means tau V. Tau V. Tau V. Nominal shear stress is tau V. Okay. So for that, so we need the effective depth. Okay. So effective depth, it is small d is equal to capital D minus cover. Capital D minus cover. So overall depth of beam it is 110 minus cover it is 30 m. Okay. So 610 minus 30, it will be 580 mm. Effective depth it is 580 mm. Okay. So nominal shear stress tau V is equal to VU divided by B into D. VU divided by B into D. B into small d. Okay. So VU factor shear force it is 180 kilonewton. Convert it is in Newton 10 raised to the power 3 divided by B it is 300 mm and effective depth it is 580 mm. It's 580 mm. Okay. So nominal shear stress it will be calculated 180 into 10 raised to the power 3 divided by 300 into 580. It will be 1.03. So nominal shear stress is equal to 1.0. Tau V is equal to 1.03 MPa. Okay. I will note down this value also. D is equal to 580 and tau V is equal to 1.03 MPa. Okay. Now step number 3, percentage of T. Step number 3, percentage of T. Percentage of T. That is in bracket PT. PT. Okay. PT is equal to AST divided by P into D into 100. Percentage of tilt over of this D. Okay. B into D into 100. Okay. So AST will be AST is 2945.243 mm square divided by B into D. B it is 300 mm and D it is effective depth is 580 mm into 100. So we get the percentage of T from this. Okay. Right. Calculate PT is equal to 2945.243 divided by 300 into 580 into 100. That will be 1.69. 1.69. 1.69%. 1.69. I will note down this value also. It is equal to 1.69%. Okay. So step number 4, shear stress in concrete. Design shear stress in concrete. Step number 4, design shear stress in concrete. Step number 4, design shear stress in concrete. Design shear stress. Design shear stress in concrete. That is in called it tau c. Tau c. Okay. So this value we will take from the I score. Actually, this value it depends upon the grade of concrete and percentage of steel. Okay. So this value it is given IS 456 page number 73. Okay. Write down as per the IS 456 2000 page number 73 and table number 19. Table number 19. Table number 90. Okay. Table number 90. Okay. So percentage of steel it is 1.69. Grade of concrete it is M20. Okay. So for M20, so it takes second column it is M20 for 1.69. Our value it is 1.69. 1.69 it will become 1.50 to 1.70. Okay. So this value will become 1.50 to 1.7. So 0.72 for 1.50 it will be 0.72 and for 1.75 this value it will be 0.75. 0.72 and 0.75. So first PT, then tau c value, and tau c value for 1.50 or 1.50. So tau c value it will be 0.72. 0.7 for 1.75 or 1.75. So tau c value it will be 0.75. 0.75. Okay. 0.75. The actual our PT value it is 1.69. 1.69. So this value to become 1.50 to 1.7. That's why we have taken this percentage. Okay. The actual what is tau c for 1.67. Okay. So we need to find out the tau c for 1.76%. Okay. So by interpolation method, we need to calculate this one. By interpolation method. So first of all, this difference 1.75 minus 1.50 divided by this difference 0.75 minus 0.75 minus 0.72 is equal to and 1.69 minus 1.69 minus 1.50 divided by tau c minus 0.72 tau c minus 0.72 tau c minus 0.72. We need to calculate tau c value from this value. Okay. So tau c is equal to 0.75 minus 0.72 divided by 1.75 minus 1.50 in bracket 1.69 minus 1.50. Okay. Then this value to become this side 0.75 plus 0.72. Okay. Just calculate this value. So 0.75 minus 0.72 divided by 1.75 minus 1.50 is equal to 0.75 minus 0.72 divided by 1.75 minus 1.50. We get 1.69 minus 1.50 plus 0.72. It will be 0.7428. Tau c is equal to 0.742 MPa. Okay. I will note down this value also. Tau c is equal to 0.742 MPa. Okay. So step number 5. Step number 5 now. Step number 5. maximum shear stress in concrete. Step 5. Step number 5. Maximum shear stress in concrete. Maximum shear stress in concrete. That is tau C max. Tau C max. Tau C max. As per the IS 456, for the IS 456 2000, page number 73, page number 73, comma, table number 20. Table number 20. Okay. So this value is given table number 20, page number 73. So it depends upon the grade of concrete. Our grade of concrete it is M20. So for that tau C max it is 2.8. Tau C max is equal to tau C max is equal to 2.8 MP. 2.8 MP. Tau C max is equal to 2.8 MP. I will note down this value also 2.8 MP. Okay. Then step number 6, check for shear reinforcement. Step number 6, check for shear reinforcement. Check for shear reinforcement. Step number 6, check for shear reinforcement. For shear reinforcement. Check for shear reinforcement. So for that, we know all these values. First of all, tau V value it is tau V is equal to, we know that tau V value it is 1.03 MP. 1.03 MP. 1.03 MP. And tau C value it is, so we need to comparison tau V, tau C and tau C max. Okay. So tau C value it is 0.742. 0.742 MP. And tau C max it is 2.8 MP. So we'll write down this here also. Tau C max it is 2.8 MP. Tau C max is equal to 2.8 MP. 2.8 MP. So just comparison this value. But here tau V it is, tau V value it is greater than tau C. Tau V value it is greater than tau C. And tau C max it is greater than tau V and tau C. Okay. Tau C max. Tau C max it is greater than tau C and tau V. Okay. If this condition, then design for shear reinforcement. Required design for shear reinforcement. Design for shear reinforcement. Required design for shear reinforcement. Required design for shear reinforcement. Okay. Then next, step number 7, shear capacity of steel. Step number 7, shear capacity of steel. Step number 7, shear capacity of steel. Shear capacity of T, that is VUS, that is in bracket VUS. So VUS is equal to VU minus tau C into B into D. Tau C B into D. Tau C B into D. Okay. So just calculate VUS. Put all this value. VUS is equal to, so VU is factor shear force 180 kilonewton. Convert it is in Newton over 3 minus tau C, it will be 0.742 into B, it is 300, and if to depth it is 580. So we get the shear capacity of T, that is VUS. Calculate this one. 180 into 10 to the power 3 minus 0.742 into 300 into 580. It will be 50.894. 50.892 will be get in Newton. Okay. So convert it in kilonewton. 50.892 kilonewton. 50.892 kilonewton. Okay. So this one it is shear capacity of T. Now shear reinforcement of step number 8. Shear reinforcement. Shear reinforcement. Step number 8. Shear reinforcement. Step number 8. Shear reinforcement. Shear reinforcement. Okay. Shear reinforcement for wide stirrup two-legged 6 mm bar. Wide vertical stirrups two-legged 6 mm diameter. 6 mm diameter. So ASP is equal to 2 into 5 by 4 6 square. 2 into 5 by 4 6 square. Into 5 by 4 6 square. ASP is equal to 2 into 5 by 4 6 square. 5 by 4 into 6 square. 5 by 4 into 6 square. So 2 into 5 by 4 into 6 square. 56.56 548 mm square. This one is ASP. Okay. Now step number 9. Spacing for vertical shear reinforcement. Spacing for vertical shear reinforcement. Step number 9. Spacing for vertical shear reinforcement. Step number 9. Spacing for vertical shear reinforcement. Vertical shear reinforcement. Spacing for vertical shear reinforcement. reinforcement. Okay. List from the following. So list from the following. List from the following. Okay. This should be list from the following. Okay. So first, there are three conditions. First it is condition one. For the condition one, first case SV is equal to first formula 0.87 into Fy into ASV into D divided by VUS divided by VUS. Okay, VUS. So VUS value we have calculated this one also. 0.87 FISP into D divided by VUS is equal to 0.87 into Fy, it is grade of steel, it is 415 is equal to ASV we are calculated ASV value 56 point something, it will be ASV 56.54 into effective depth, it is 580 mm divided by VUS. VUS it is 50.892 into 10 raised to the power 3 Newton. So SV is equal to 0.87 Fy, it is 415, ASP it is 56.54 into 580 divided by 50.892 into the 10 raised to the power 3. It will be so this value will be 232.649 mm. Okay. Condition 2, SV is equal to 0.75 D, 0.75 into D, 0.75 into D, it is 580 mm. It is 580 mm. 0.75 into 580, it will be 435 mm. 435 mm. Then condition 3, it is 300 mm. Condition 3 is SV is equal to 300 mm. List from the above value. Spacing should be list from the above value. Spacing should be list from first, comma, second, and third. So which one it is spacing? The spacing it will be 232. So SV is equal to 232 mm. So round the figure it will be take 230 mm. Okay, 230 mm. Now check for minimum. Yes, minimum spacing. Minimum spacing minimum spacing should be SV minimum is equal to SV minimum is equal to 0.87 into Fy into ASV divided by 0.4b divided by 0.4b 0.4b 0.4 into b 0.4. All this value is equal to 0.87. Fy it will be 415 into SV it will be ASV it will be 56.54 6.54 divided by 0.4b divided by 0.4b 0.4 into b it is 300 mm. Okay. SV is 0.87, Fy it is 415, ASV it is 56.54 divided by 0.4 into 300. It will be 170.11 mm. Okay. So ASV value it will be greater than SV minimum. Greater than SV minimum. So provide two-legged vertical stirrups at spacing at 230 mm center to center. 230 mm center to center. 230 mm center to center. This unit is design of shear reinforcement when tau b value is greater than tau c. Okay. So for design for a shear reinforcement. Okay. Design for the shear reinforcement.